Okay. As Victoria said, this will be a two-part presentation, and Wieslaw and I are here actually representing a very large team of people, and you'll see that list of people shortly. The Marginal Ice Zone program was the first in a new series of Arctic programs for the Office of Naval Research, and I'll show you that progression as well. But it was started out as an ONR program with a fairly large international component, and that grew. The picture you see is actually from the Aeron. One of the hallmarks of this program was it was supposed to be all autonomous. We were told at the outset that we would have to do this without heavy support, without icebreakers and such. But the Koreans came in late in the game and offered us a very generous dollop of icebreaker time and aircraft time to work further up north. And so we used that to get further north than we'd originally planned to go. But it was a very nice collaboration in many respects. So because I don't know where everybody is at in terms of their knowledge of the Arctic, I thought I would start with a few motivational slides. You read a lot about the fact that the Arctic is changing very rapidly at this point, right? The loss of sea ice is the thing that's most prominent and that you see in the news quite frequently. And indeed, the sea ice is declining very rapidly. That's largely coupled to just a general rise in air temperature. But it's not just the sea ice extent, it's the nature of the sea ice, the characteristics of the thickness. So there's been a dramatic reduction in thickness. So an overall steady decline in sea ice volume. And the sea ice is largely first-year ice, which makes it more fragile, more mobile, right, more malleable than the multi-year ice of previous years. With that come many different effects, right? You have the melting of land ice in Greenland, increase in upper ocean freshwater content. We think we're beginning to see the release of that freshwater into the subpolar oceans. We don't yet know what the impacts will be, but there's plenty of speculation from model results about what may happen. And with these things come some changes in the physics, right? We think we expect to see a change in the balance of the physical processes that are important in the Arctic. We think we may see new feedbacks rise in importance. The ice albedo feedback is perhaps the most famous one, right? The idea that snow-covered ice is very reflective, so it protects itself. But as soon as you get ponding or melting and you get darker areas, those are more readily absorb solar radiation, which means they warm, which means they melt, which means they form larger dark areas. And so you have a positive feedback. There are also negative feedbacks that are present as well. And so one might ask how the balance of those feedbacks changes as we see these changes in sea ice and as we see the warming. I've been really interested in what we see in terms of secular trends, long-term trends, kind of a climate scale measurements. Many people are interested in the increase in seasonality, physics at other time scales that we see changes in. So all these things are changing, and the physics are changing, and we perhaps have a less than perfect understanding of what's important and what's not. So every program has a governing cartoon, a favorite cartoon, and this one was ours from the Marginal Ice Zone program. And it's actually been carried forward into new programs. And if you look at this cartoon, the left-hand side is meant to represent a largely ice-covered ocean. And as you move to the right, it's meant to represent a largely ice-free Arctic. The Arctic is upside down in that it's cold and fresh, shallow in the upper ocean, warm and salty below. And that's important because that cold, fresh halocline protects the ice from the supply of heat from the warm, salty water below. And that warm, salty water comes from a few different sources. If you go deep, it comes from the Atlantic inflow, coming through Fram Strait, primarily. If you go a little bit shallower, it comes from Pacific water, then enters through Bering Strait. And shallower still, it may just be radiative warming from the previous summer that's been trapped below a fresh halocline and that will be released at some point later in the autumn. And that can play a role in delaying freeze-up, so it can play a role in the timing of the sea ice extent. If you look at the left-hand side, you see the little melt ponds, and that's meant to illustrate the difference in the openings, the leads in the ice. And those areas are dark and are good at absorbing solar radiation, so they can warm pretty well. The other areas are reflective, and so they don't really absorb much solar radiation. When the ice is present, when it's pack ice and not very mobile, communication between the atmosphere and the ocean is fairly weak. The transfer of momentum is fairly weak, and the coupling is weak. So it's quiet, not much internal wave generation, not much mixing. But as the ice becomes more mobile, the momentum transfer may become more efficient than it is in open water. And so we might see very dramatic internal wave generation. We might see turbulent mixing in those partially open areas. As you get more open water, you can generate very strong areas of shear and surface wind stress, going from very efficient transfer, say in partial ice, to less efficient transfer in open water, to very inefficient transfer and then less mobile ice. And as you go into open water, we think that surface waves may become important. This is one of the focuses of the MIZ program. The idea that as you get increasing fetch, increasing open water to the south, there's the ability to generate long period surface waves, and that those waves might be able to penetrate into the marginal ice zone and mechanically break up the ice. That would give you the kind of smooth marginal ice zone where you see smaller flow sizes towards the edge and increasing the large flow sizes back into the pack. And the waves are propagating in and breaking those up. And that was one of the questions, whether this was happening in the New Arctic. So this slide, which is it's a slide from one of Andrei Porshentinsky's papers, but it was just meant to illustrate the fact that we talk about climate, we throw that word around a lot, and in reality we're not doing climate here, right? Climate is a 30 years for a point, 30-year mean sort of thing, and what we're really looking at is trying to get at the processes that drive seasonality and might go into impacting the longer time scales, but we're not really observing at those scales. Important to observe at those scales, and we've been trying to get at that part through different channels. So the challenges we face in doing something like this, the ice represents a pretty obvious barrier to making observations, right? It's made it difficult. In previous years, we've used the ice as a platform to hang things from, which is great. It's a very stable platform to hang instruments from. They drift, which is challenging. And these days, it's getting harder to land on the ice to do that with aircraft. We'd like to be able to measure multiple domains simultaneously, so atmosphere, ice, and upper ocean. We can typically do a couple of those, but not all three at once across the interface. It's difficult to maintain a presence for long enough, and being Lagrangian in one of those frames is not the same as being Lagrangian in the other. You have a reference frame issue depending on where you decide to tether yourself. Resolution is an issue. The deformation radius is quite small here, and when things are really moving, when things are energetic, we believe sub-mesoscales are active. We know that there are strong mesoscale eddies in the Arctic, even when it's fully ice covered. So in a sense, we have fully 4D physics that we're trying to resolve. We probably need to be persistent across the melt and freeze-up seasons at least to be able to see the range of processes. And in order to do that, we need to be able to put out lots of platforms. So we need to be able to deploy scalable systems. ONR has been working at this, as I say, over a number of different programs. You can imagine the kind of thrust that they have in terms of their development. They're interested in producing new technologies and approaches for observing the Arctic, for maintaining a presence, for making those observations, just a basic improved physical understanding, and then eventually driving that into Arctic system models that would have some predictive capability. There's been a revolution in autonomous observing that we've been exploiting. Everybody's well aware of the Argo program, right? Lots of 4,000 profiling floats through the world oceans, gliders, other autonomous platforms. In the Arctic, we have a range of platforms that we mount on the ice that measure waves on the ice. They measure ice mass balance. So looking at snow and ice and the processes that control the melt of that snow and ice. Automated meteorological measurements are a weak point. We don't really do them well at all. Particularly flux measurements in clouds, we're pretty helpless to do that in an unintended fashion. We can do them for short periods of time, but longer periods are still something that's beyond what we can really do. We have a variety of measurements that we can do using the upper ocean that either drift or they're mobile and they profile. We can do acoustic navigation to geolocate those platforms, and we've been able to sustain those kinds of things for periods of a year. Not easily, but it can be done. And then we rely a lot on remote sensing, both for situational awareness and for monitoring the ice. So we can actually follow platforms around, document the changes in flow size distribution and ice properties over a period of time with sufficient quantity of remote sensing and targets to track on the ice. So this is the progression of ONR research initiatives. The Marginal Ice Zone is the one at the very top, and that was the first one. Another one that you would probably like to hear about at some point is the Waves and Sea State Initiative, which is really Marginal Ice Zone focused on the melt period, Sea State focused on the freeze up. Stratified ocean dynamics is what we're doing right now, which is focused on the upper ocean. So really, these are all sort of different facets of the same system, a slightly different focus. Stratified SOTA is really trying to do an annual cycle, where the other two were focused on individual periods. So this is the Marginal Ice Zone experiment. If you look on the left-hand side, you see a long list of capabilities and people, and that's kind of what was required to do an experiment of this size, spanning ice, ocean, and a bit of atmosphere, and the kinds of things we needed to do. This was motivated by the rapid sea ice decline in the Beaufort Sea and the increasing importance of the Marginal Ice Zone, where you went from having a very small seasonal ice zone and a marginal ice zone that might have been of limited importance to having an enormous seasonal ice zone and a huge part of the region be marginal ice zone. So the thought was, for the first program, let's take a look at the marginal ice zone during melt and see if we can understand some of the processes that are controlling that melt back. In particular, the fact that the models were under-predicting the rate of that melt. So the actual decline of sea ice extent is happening much more rapidly than the models are predicting. The observed decline is almost outside the one standard deviation envelope of the model ensembles. You can find results from the MIZ program in a special collection on Elementa, which embarrassingly is still accumulating papers. We're still dribbling them in after quite a bit of time, but there are a few more that still need to land there. And then there are other papers scattered throughout JGR and other journals. We're trying to collect a comprehensive bibliography on the project website, but the Elementa volume is a good starting place. So quickly, the idea was we would put down a carpet of instruments ranging about 400 kilometers north-south, a combination of instruments drifting on the ice to measure waves in the ice, to measure ice mass balance, and to do profiles, ice tethered profiles, doing profiles in the upper ocean. As the ice melted back, we would always have these measurements that were near the ice edge and then progressively far away from the ice edge. In these clusters, it would tell us something about wave number and properties of the waves propagating through the ice. And then we have mobile platforms, gliders, that were marking back and forth between the open water, through the marginal ice zone, and deep into the pack to try to tie all those things together. Some floats and some traditional moorings further to the south, and some wave gliders. So roughly 100 assets deployed, mostly using aircraft. Lightweight camp, like you see in the bottom photograph there. 2 twin otters, one from Bass, one from Kemboric Air, and one Bell 412 from Great Slave Helicopters. And just mountaineering tents. So rather than setting up a little village, we were just putting people out on the ice for a night. Thanks to good weather, we were able to get all the instruments out in a week of time, which is really remarkable. The top was meant to be a movie, but it's not a movie. We don't have it. But what you would see is we deployed that nice, neat line of instruments that you saw. And then over the course of the experiment, that line deformed from being a north-south line, from being a meridional line to being a zonal line that was stretched out in the east-west direction. We knew we'd see some rotation like that, but the ice was more mobile than any of our previous looks at the ice drift would have led us to anticipate. It actually worked out all right in the end, but it didn't give us the really nice north-south stretch that we were hoping for. So really briefly, some overviews of results. These are results from Phil Wang. Phil concentrated on the remote sensing imagery and also on the ice mass balance, but this is from the remote sensing. It's actually remarkably hard to do automated identification of flows. In particular, this is what you need to do if you want to be able to do classification of flow size distribution, and then look at that as a progression over the course of a year, say, following one of these clusters, which was exactly what we wanted to do. Phil developed algorithms for doing flow size distribution automatically. Applied that to the various remote sensing time series over the different clusters. The primary result of this is that he took a look at what was going on during winter, the formation of leads and cracks, traced that back through to the summer, and at least in the situation that we're seeing, and you'll see why in a minute, a lot of the flow size distribution in the summer was set by what happened during freeze up and during the winter in terms of the formation of cracks and leads. They had a large influence on what happened during the subsequent melt season. So the next slide is a result from Jim Thompson and his students, Maddie Smith and Seth Zippel. And Jim was focused on surface waves in the Arctic, and in particular the surface wave impact on the sea ice. And what you see if you look at the left-hand side is wave spectra, frequency in the horizontal axis and energy in the vertical axis. In the ice, in the dashed lines, and off the ice, in the on ice winds in the dashed lines, and off ice winds in the solid lines. And you see that for off ice winds, there's considerably less swell. For on ice winds, you get more swell and more high frequency waves. If you look to the right at the top panel, the images are meant to show you where these measurements are made. But if you look at the spectra in the top panel, plotted as a function of ice fraction early in the season and later in the season, where the colder colors are larger ice fractions and the warmer colors are smaller ice fractions, more open water. What you see is a damping of the higher frequency waves as you come into even a couple of tenths of ice. You start to see this damping, and the lower frequency waves, the energy can propagate through, but there's not much of it, and you'll see that in a minute. And essentially what this is saying is that when you have higher frequency waves entering the marginal ice zone, they dissipate very rapidly, right? They expend all their energy moving little pieces of ice around at even a couple of tenths, and they don't make it very far into the MIZ. And you can see that in turbulence as well if you look down at the bottom panel where turbulence in the upper half a meter is greatly damped with the presence of any ice at all relative to what they see in areas where there's open water. So the story there is the ice protects itself from the high frequency waves. And then if you look at these results from Jeremy Wilkinson and Martin Doble, looking at surface waves and sea ice, if you look at the bottom panel, really is the one to concentrate on. Its significant wave height is a function of time. And if you think of around September 15th as being the sea ice minimum, so that's when there are vast expanses of open water, the melt is basically done and freeze up is going to begin again. The thing you note is that there just aren't big events prior to that sea ice minimum, right? So they're just, and we see that in the spectra as well. There were no long period waves penetrating into the pack. There were no long period waves, period. So it's not mechanical breakup, at least not in 2014. There was influence in the melt. It was really thermodynamic. And that's what you get from Scott Gallagher's results, where he's looking at results from autonomous ocean flux buoy. So these are ice-tethered instruments. They're meant to measure microstructure mixing in the upper part of the water column and a bit of a profile through the water column as well. Sean divides this up into several phases, looking at the springtime mix layer, the period where you have melting, so the mix layer is warming and freshening, a summertime mix layer where you have radiative warming, So you have solar radiation that's penetrating below a fresh surface layer, which you see labeled halocline there. That heat is all concentrating in the subsurface layer. And then later in the season, when you start to get into freeze up, which isn't plotted here, that heat is released back into the upper part of the water column and can delay a freeze up. But the thing that you see from Sean's results and from Jeremy's results and Ted Max when we were doing the ice mass balance is that basically it's a thermodynamic melt. The story is that the sun shines, the atmosphere gets warmer, and the ice starts to melt. And you could see that when we were up there, and that the ice was all melting at once over hundreds of kilometer spans. You just had this lattice work of ice and melt ponds, as opposed to the nice, neat, tidy progression of small flows, larger flows, still larger flows, pack ice, which is what you might see in say, the Greenland Sea, right, where you've got an ice-organized marginal ice zone. And with that, I think last part for this is just glider sections. I think we're running late, so we're working on this part, but we have many sections spanning ice, open water, and marginal ice zone. We see enhanced variability in temperature and salinity along isopycnals associated with the ice edge, and it tracks the ice edge because the gliders are following the ice edge. We're relating this to essentially small-scale mixing lateral stirring processes. And with that, I'll hand it over to Wieslaw. Wieslaw, I can flip the slides for you. Just let me know when you want to.
Okay. I don't know if we want to take time for questions for this part. And the other question I have, how much time I have? Because it was supposed to be 30 minutes, we're already 25 minutes into the hour.
Yeah, so technically you only have 5 more minutes, but you can go over a little bit if you have more to cover. That's fine. Okay,
I can skip some of those, but so the idea is that there were 3 modeling groups involved in the ONR-funded Marginal Ice Zone project. And the good news is that those teams have been involved, were involved in the project from the very beginning, including the putting together the science plan and then maybe motivation and some rationale for what to measure and what is possible given the current technology. And as Craig outlined, the approach that we didn't want to involve in this project any heavy icebreakers or heavy ships. It was all mostly autonomous underwater vehicles. So the main thing was that to understand the marginal ice zone processes and feedbacks within the bigger picture, how those processes and feedbacks within this region in Western Arctic marginal ice zone contribute to the bigger picture of ice declining in the Western Arctic and a couple climate representation of this new regime. In particular, the ocean stratification was basically under the microscope, as you saw from a few last slides that Craig presented, looking at the mixed layer depth, halocline depth, near surface temperature maximum, different water masses, Pacific summer water, Pacific winter water. In the end, trying to better understand the heat and freshwater content in the Western Arctic in presence of the ice or in absence of the ice across the marginal ice zone. Comparing models against the observations for the purpose of evaluating model and finding possible ways to improve it. I have one slide which is summarizing a paper by Jin-Lung Zhang and colleagues regarding the flow size distribution representation in a model combined with the ice thickness distribution. And in the end, we've done a lot of work as a group in terms of looking at the coupling across the surface between the atmosphere, sea ice, and ocean in terms of the ice roughness at the surface, ice roughness at the bottom, the momentum transfer in presence or in absence of ice. And as you heard from Greg, very low presence of ice, very low concentrations will significantly dump the surface gravity waves, which might modify the amount of momentum transfer from the atmosphere directly to the ocean where there is no sea ice present or in the open water fraction of the ice area. In the end, the idea is that would like to improve those models for forecasting sea ice, forecasting in terms of maybe shortwave forecasts. So that's the reason why there was an NRL group with Pomposi representing that part of the forecast goal. Prediction and projection is more like improving models for climate prediction and climate projection at longer timescales beyond operational. Next slide, please. So one overview slide of our model. Not sure if I showed that slide a year ago. Basically, we have a version of a regional climate system for the Arctic, which is very similar in configuration to the community Earth system model, with the sea ice and the ocean and the coupler component identical with the previous version of the CSM, including marine biogeochemistry, as a matter of fact. But for the atmosphere and land hydrology, we went with the regional version of those models, being the weather research forecast and the variable infiltration capacity VIC model. And on top of it, we have a routing stream flow taking water from land through the coupler to the ocean. So we're predicting the runoff from the land into the ocean and not prescribing it. Different model configuration. The important thing is that for the regional model, philosophy is that we are trying to increase the resolution to represent the details that require that high resolution, both in space and time. And that's possibly one of the motivation rationale for regional modeling in general, to understand the process feedbacks, a bigger picture, and provide guidance to the global climate models for future development and future improvements. Next slide, please. So one slide with regard to optimizing modeling parameter space. What we've done here is that we've used the same model with just changing the value of one or two parameters in the sea ice parameterization and decoupling of the momentum transfer parameterization. The top panel is showing the ice extent from 5 different experiments, and don't worry about trying to differentiate them or understand the values. The bottom line from that top panel is that with those changes in the parameter space that we run tests with, we don't see much of the variability of response in ice extent. However, if you go to the middle panel where we're showing the volume changes time series, you can see that between the red and blue experiment, we basically have twice as much volume in the red compared to the blue experiment. At the same time, we have almost no difference recognized, or a significant difference in the ice extent. So most of the difference in volume time series in those two extreme experiments is related to the ice thickness. The bottom two panels are showing the ice thickness in September for 5 years, 2000, 2004, where the left panel represents the red experiment with too much volume, basically overestimated, and the lower right panel is showing the blue experiment, which is probably more realistic to what we expect from the satellite estimates of ice thickness distribution during that time. The main thing is that in both cases, the ice extent looks very reasonable compared to the green contour, which is the passive microwave from satellite for September 2000, 2004. So the bottom line from this plot is that if you don't optimize your parameter space, you might end up having completely different, unrealistic or more realistic ice thickness distribution. And if you're concerned about using those kind of sea ice states for your prediction, forecast, projections, or longer term prediction, your ice thickness will affect what you predict into the future, whether on the short time scales or on the longer time scales. The other message or take-home message from this is that the ice extent is not sufficient metrics to evaluate the climate models, because you can have a reasonable ice extent, but you can have a completely wrong ice thickness distribution, which will affect your climate simulation and prediction. Next slide, please. So here we're showing basically how well we can optimize that model. The left panels are winter and summer, March, September 2007, one of the, second lowest minimum ice extent represented by green contour in all panels. And what we're showing here is that the green contour represents the ice extent from satellites, 15%, and the end of the shading, which is closed with the black contour from the model, showing agreement and maybe still some discrepancy for this particular winter and summer of 2007. When we go to the right panels, it's called GV2, same September and March 2007, but now we're using high resolution model configuration. The left one, ice and ocean, was about 9 kilometer grid cell. The right panels are representing 2.4 kilometers. You can see that not only we have similar agreement, but we have reduced some biases that have been still present in the 9 kilometer simulations representing that particular winter and summer of 2007. Some of the discrepancies are further reduced. So basically there's an improved scale, not only representing the ice thickness distribution with high resolution, but also we can more favorably compare against the observations of the ice extent. The lower panel is basically showing a comparison of ice extent anomalies between the model in red and the passive microwaves from satellite in black. You can see that we have both seasonal interannual variability as well as the recent trend, including the minimum of 2007 September, represented both by the black and red line from observations in the model. The take-home message is that this doesn't happen automatically. The G9, the left panel results at the top, are after about 40 simulation experiments where we try to optimize the parameter space to get the best agreement for the past and present, which we argue is important to derive initial conditions for shorter and longer term forecasts and predictions. Next slide, please. So this slide is basically showing that based on observation, there's a very nice paper by Mary Louise Timmermans, 2018, and colleagues where they show that in the Western Arctic, this yellow diamond north of Alaska, in the Beaufort Sea, there was the profiles are representing profiles over different time periods from this yellow diamond. You can see that between 1992 and 2015, basically a significant increase in shallowing of a warm water layer in the Western Arctic over that time period. If you calculate the estimate of the heat content, basically almost doubled heat content in the upper Western Arctic Ocean, where the marginal ice zone have been taking place several years earlier, 2014 in particular. The heat content estimate from about 2 times 10 to the 8 joule per meter square went up to 4.2, 10 times to the 8 joule per meter square over that basically 30-year period. 30-year period. And the lower panel is showing a model results where we look at the model estimates of the ocean heat content anomaly shown time series in red, and the ice extent anomaly shown from the model in purple. You can see clearly that there is a correlation. Whether this is causality and result is to be determined. We have some publications suggesting that, but basically the more heat in the upper ocean in the Western Arctic simulated in the model, the ice extent anomaly significantly declines or goes negative over that time period of simulation. So there's at least some hints from the observations and the modeling results that proper representation of the upper ocean heat content might be important to more realistic representative of the ice decline in the Western Arctic in particular. Next slide, please. This is showing some of the processes. I can skip some of it. Maybe next slide so we can go faster. But representing the freshwater content accumulation in the Western Arctic, the red warm colors represent roughly about 25 to 30 meter equivalent of freshwater accumulated in the Western Arctic for, in this case, from the model for July 2007, which is in quite good agreement with observational estimates from the Beaufort Gyre experiment, where they have multiple mooring location in this region, estimating a similar equivalent freshwater thickness in the Western Arctic for that time. Next slide, please. Maybe we can skip that. Basically, we're showing that there is a lot of eddies and stuff like that. So representing eddies in the Arctic is important. High resolution to represent eddies is critical. And if you are concerned about the Western Arctic ice decline, the representation of the Beaufort Gyre dynamics and eddies working, communicating the shelf water across the continental slope into the marginal ice zone of the Western Arctic, interacting with the Beaufort Gyre circulation for sea ice in the upper ocean. All these processes are critical to be represented well in the ocean and sea ice models, and the high resolution is required to represent. Next slide, please. So basically, those are cross-sections from some of the lines from the previous slides, and the switching dashed and solid contours in the vertical represent basically incoming and outgoing velocity, which are representing mesoscale eddies within the Beaufort Gyre. And the top panel, the black line, represent the sea surface height, showing that the Beaufort Gyre is a dome of fresh water in the middle, in the center. And because we have a mass of a length of fresh water with some additional weight, the iso picnals are basically lowered in the center of the gyre, and those eddies, mesoscale eddies, are trying to level those isopicnals along the perimeter of the Beaufort Gyre circulation. Next slide, please. This slide is basically a first estimate from our model of the eddy heat flux, lateral eddy heat flux on the left. So basically, we take the product of U prime and T prime perturbation of the temperature and salinity, temperature and velocity in U and D direction, and over some time period, average that heat flux, eddy heat flux will provide the information of the heat perturbation with the velocity perturbation communicated in a particular direction. So basically, warm water from the Chukchi Shelf and the East Siberian Shelf is penetrating across the continental slope into the marginal ice zone of the Western Arctic. And the right panels are the estimates of the ice age in this particular case for March and September 2012, the lowest ice extent recorded by satellite up to the present, where you see that the very old and which is proxy for very thick ice disappears 6 months later between March and September. And there's no way that the atmospheric melting from the top can only account for this melt. You need to have help from the oceanic lateral and under ice melting provided by this eddy heat flux as represented on the left panel. And for that, you need to have eddy resolution, which is basically order of a few kilometer grid cell for the ocean and sea ice models. Next slide, please. We can go to the next slide probably to save time. I'm happy to talk about this, but I realize we're 40 minutes into the presentation. So basically, this is a summary of a paper by Jinlun Zhang in terms of incorporating the flow size distribution into the model, sea ice model, which already has the ice thickness distribution. The flow size distribution can be quantified by something called cumulative flow number distribution, CF&D, which can be compared against the similar estimates from observations such as Craig was showing the remote sensing TerraSAR-X satellite images that have been produced and analyzed by other colleagues within the MIZ program funded by ONR. Simulated mean flow size average over all ice-covered regions and shows no annual cycle. Shows an annual cycle with large flow size in the winter and smaller in summer. However, within the marginal ice zone, there is no annual cycle. Flow size distribution results in reduced marginal, it causes the reduced ice thickness in the marginal ice zone. So without that parameterization, you are likely overestimating ice thickness in the marginal ice zone. Related to the more form drag related to the multiple ice flows parameterized in the sea ice model, which helps with the coupling momentum and basically causing more mixing in the upper ocean, exchanging warmer water from below to the bottom of the sea ice. which means that the simulation with the flow side distribution will yield improved representation of the ice extent and the earlier ice retreat. Next slide, please. This is something that maybe was what Craig was looking. The upper right panel is basically a drift of the instruments as observed by the satellites, and the ice thickness shading, color shading, is the ice thickness from the cryosat provided by Alfred Wegener Institute. So basically, in the beginning, you can see that most of the assets, those multiple arrays, were aligned roughly along the longitude line in the eastern Beaufort Sea, and as the drift progressed and the marginal ice zone evolved, it became much more zonal over time. The circles representing the initial time of deployment, and the squares are representing the some later part into the fall where those assets ended up drifting. The other panels, the right and the bottom panels, are representing three different models: the University of Washington MIZ, the NRL Global Ocean Forecast System, and our Regional Arctic System model. The MIZ, I believe, and the GOFs, they are assimilating ice concentrations, so they have a little better representation of the ice drift. But if you compare the ice thickness between the upper left observations and the lower right from the RASM, you can see that actually RASM quite well represent the ice thickness in the Beaufort Sea in general, with relatively thicker ice in the southern Beaufort Sea, which might explain that in RASM, the assets deployed there as simulated by the sea ice drift are not moving as fast as in comparison with observations in the upper left. So there's some still room for additional improvement and additional parameterization. One of them would be the more realistic representation of the momentum coupling from the atmosphere through sea ice to the ocean, and better representation of the ice thickness distribution, possibly including the flow size distribution as demonstrated by Jinglun Zhang and his colleagues at the University of Washington. Next slide. I think we can skip that. I talked about this a little bit last year in terms of developing the initial conditions for the forecast in RASM, and the next slide is basically showing those results for forecast of the past, basically 6 months forecast starting April 1, 2016, and forecasting the mid-September 2017. The main message from those slides is that both initial conditions and the forecast in RASM, which is here on the lower left, are significant improvement to the ice thickness from the NCEP CFS reanalysis, both for reanalysis as well as the forecast, which is the upper right panel, upper left panel here, ice thickness distribution for the CFS V2 forecast 6 months after April 1 initial conditions. And the lower right panel is basically showing you a different color scale, but estimate from the cryosat composite over a three-week period, focusing on the mid-September or late September. So you can see that RASM has much more realistic ice thickness distribution compared to the cryosat in the lower right, compared to the upper left NCEP CFS V2 having way too thick ice and too much ice in the Western Arctic. Next slide. So in conclusion, with respect to the marginal ice zone, eddy resolving Arctic Ocean models are necessary to resolve the critical processes such as eddies, coastal and boundary currents, sea ice deformations, realistic representation of the shelf basin exchange, which in part is driven, or major part is driven by the eddy fluxes across the continental slope, communicating both Pacific summer and winter water from the Chukchi Shelf into the Western Arctic marginal ice zone, helping develop that marginal ice zone, both melting ice laterally as well as entraining water under the ice and reducing the ice thickness. Improved estimates of the freshwater and heat content within the Beaufort Gyre are critical in order to understand the ice thickness distribution and predict the ice in the future. The resulting ice-ocean feedbacks, such as I was discussing, the momentum transfer present of ice, and the very high efficiency, at least in the spring marginal ice zone development, of the low ice concentration, very efficiently dumping any surface gravity waves, and how this is helping or limiting the momentum transfer between the atmosphere and ocean, basically slowing the sea ice. Improving the sea ice models, such as the different rheology and deformation representation of the form drag, the roughness from the surface and the bottom, for better momentum transfer and representing of the sea ice state for initial conditions and forecast. Incorporating new processes such as Greg alluded to, ice wave interaction, which is not currently represented in any of the models to my knowledge. And then better improved ice-ocean coupling, better validation, better data sets such as available from MIZ are much more important to look at processes, mesoscale and sub-mesoscale processes, related feedbacks and their different time and spatial scales. In the end, trying to reduce uncertainty in representing the initial conditions and improving prediction for climate models. I'll stop here.
Great, thank you, Wieslaw and Craig. Did you want to go on to questions and answers?
I'm happy to answer any question. I'm sure Greg too.
Okay. So if any of you guys have questions, feel free to take yourself off mute. You can also type the questions into the chat box and I can read them out loud. And if you have difficulties taking yourself off mute, send me a message and I can try to manually do it from my side. So with that, go ahead with any questions.
Hi, this is Antonietta. I have a question for Wieslaw. Anyway, thank you to both of you for these very interesting presentations. So my question concerning the model is, I think it's very interesting, this accumulation of heat in the Beaufort Gyre that the model shows. And so one question I have is, do you think that is due mainly to local processes like vertical mixing, or to what extent is due to advection from the Bering Sea advection processes? Which then leads me to another more technical question. So how do you initialize your model, and how do you spin up your model, and what do you use for your lateral boundary conditions, which would affect advection from like the North Pacific, for example?
Okay, few parts question. I'll try to answer the first one. I do confirm that we believe that the accumulation of the heat in the upper ocean in the Beaufort Gyre might be a very important and critical component, which is not well represented in many climate models for a number of reasons. One of them, or some of them, might be related to the ocean resolution. Some of them might be related to the communication from the Pacific to the Arctic Ocean across a very narrow and shallow Bering Strait, which has to be somehow basically tuned in coarser resolution ocean and climate models because there is not enough resolution. So it might be representing well some past conditions, but maybe not more recent ones. In terms of the importance of the heat, the idea is that we believe, our group related to this modeling activity, we believe that not only the resolution, but also parameterization of the momentum transfer from the atmosphere into the upper ocean, and then potentially over-mixing due to the existing parameterizations like KPP parameterization in the upper ocean will not well represent the upper ocean structure in the Western Arctic, and will overestimate the thickness of the mixed layer, will remove the warm water accumulated through the local solar insulation, as well as advection from the marginal seas such as Chukchi and East Siberian seas into the Western Arctic. So I'm answering also another question, part of your question. We believe that both processes are critical. Local solar insulation by absorption of the short wave by reduced ice cover and increased open water fraction with lower surface albedos but also the advection of the warm water from the shelves, where the ice retreats a few weeks earlier now compared to the previous decades. So there's more accumulation over the shelf of shortwave, and this warm water from the shelves across the shelf basin interactions, eddy fluxes, gets communicated both into the marginal ice zone, into the ice edge, but also, I skipped that slide in my presentation where we show that some of those warm water lenses coming from the shelf, they go underneath the ice and start melting the ice from below, reducing ice thickness, and then reducing the ice extent and concentration in the following weeks or months over the summer melt. In terms of the technical question, initialization and spin-up, in our case, we run order of 80 to 100 year spin-up with the ice-ocean model only, driven by multiple cycles of the reanalysis, such as NCEP or ERA interim. And then we use those initial conditions from the ice-ocean spin-up to run production simulation with a fully coupled atmosphere-ocean sea ice land hydrology. But we still will go all the way back from 79 until present, and then we use this production run like a hindcast without any bias correction, without any data simulation, use it as initial condition for forecast, as I presented briefly, the past forecast of September 2017, initialized on April 1, 2017. I'm happy to discuss this offline or in person or later on in detail, but I think that this is my answer at this point.
Yeah. And what about your lateral boundary conditions?
So the lateral boundary conditions are only prescribed for the atmosphere. We go way out into the mid-North Pacific and mid-North Atlantic, 30 north in the Pacific, North Pacific, 40 north in the North Atlantic. So we basically have a monthly climatology from the so-called PHC climatological TS atlas, and we do not modify the. We don't have interannual or decadal variability along the lateral boundary. Basically, we'll argue that the mid-Pacific, mid-North Pacific, and mid-North Atlantic, driven by realistic wind forcing, daily interannual decadal forcing, provide the reasonable, and we have number of references, papers published on the fluxes across Bering Strait, Ram Strait, inflow into the Arctic from the mid-latitude ocean, that we have a quite reasonable representation of interannual and long-term decadal variability and trends. So we believe that having climatology, boundary conditions in the ocean does not affect our representation of the interannual decadal variability of the central Arctic and the sea ice evolution in time.
Okay, well, thank you.
Any other questions? Feel free to speak up.
One of the issues that, this is Victoria, excuse me, one of the issues that you guys raised in the pre-workup had to do with providing the data from the experiments. Have you had some challenges with using the new types of autonomous floats and profilers in integrating those observations into moving them into archiving systems, or has that gone fairly smoothly?
The problem there is of our own doing, that we meant to collect the data. We want to collect it as a complete data set, just because the synergy of having all these measurements together we felt was powerful. And we need to do it. We meant to do it last year, and it hasn't gotten done yet. Jim Thompson has, I think, pioneered a very nice path for doing that through UW for C-State. So the current plan is to pick Jim's brain and actually follow that. But I think we're going to be okay for the kinds of data that we have, based on his experience with C-State.
That's great. The one other, I know we're running over time. I just was thinking in terms of generally, a lot of the modeling improvements have stemmed from higher resolution. And I think that you guys also made the point that parameterizing the models was for the particular region was really key. Do you have any information on how those parameterizations translate as you move into higher or lower resolution, whether they're fundamental or whether they have to be re-parameterized with different resolutions? I mean, they usually do, of course.
Yes, so the answer is it's both. They need to be re-parameterized, or basically improved parameterizations might be necessary, for example, to better represent the Arctic mesoscale eddies. But our experience with optimizing our models and comparing how global climate models behave, such as NCAR CSM or a number of other ones, UK Met Office or Norwegian climate models. There are a lot of parameterizations that basically could improve the existing climate model simulations of the Arctic climate and sea ice. However, this optimization is not common across modeling communities. For example, one good example I can provide you is that a lot of models will have basically a very thick ice in the center of the Beaufort Gyre in the Western Arctic, which to me quite clearly suggests that the ice is moving too fast and converging with the Beaufort Gyre clockwise anticyclonic circulation of the Beaufort Gyre basically accumulates in the center. That's not realistic, but modifying some parameters within the sea ice model, such as the ice trend, which is basically, or equivalent to ice trend, which is basically controls the amount of energy which is diffused or dissipated by frictional effects within sea ice versus how much energy goes into moving ice. And this is a very important parameter we found, for example, in our case, where we can, the red and blue experiment I show you was twice as much volume between the two. One of the parameter was related to the equivalent sea ice strand, internal ice strand, which controls the dissipation of energy by friction. So there is ways to improve the existing models with existing parameterizations, but some of the parameterizations to represent, for example, lateral eddy heat flags across the shelf basin boundary along the continental slope might require basically pure increase in the high resolution, which my argument on that also is very, very maybe different than other people. Within the computational geophysics, a lot of people are currently talking and getting ready for something called exascale capability, which is an order of a magnitude increase computational resources and the speed of those resources. So we need to also focus on developing models, climate models that can use high resolution, but can take also advantage of available or incoming computational resources and not be very slow on those new computational architectures, such as exascale architectures, where climate models typically can get order of 5 to 7% of the peak CPU speed. So we need to improve the efficiency and computational effectiveness of the calculations within climate models, and not necessarily complain that we cannot go to high resolution because we cannot afford the computational resources.
Thanks. Well, we're running a little bit over time. If people don't object, maybe we can go 15 minutes over and kind of close up now, and then have our panel discussion after we thank our speakers. Thanks.
Well, just a quick question. This is Mike. Thanks, Craig and Wieslaw, for your presentations. Just really quick, so this MIZ has wrapped up from what I can tell, and there are still some papers being written. In terms of your legacy, you've got this special collection. is there also a comprehensive capstone article that summarizes the objectives, lessons learned, unexpected outcomes, and next steps for the community that you're planning, particularly one that ties together the observational and modeling aspects of the project?
So this is another embarrassing admission. I have a partly written BAMS article. It was meant to go out at the same time as the elemental collection hit the street, or at least the bulk of it did. And I think at this point that, you know, what I'm hoping to do is to change that a little bit, use it as a summary of our results and the program, and submit it to BAMS still. Yes.
And then along those lines, what would you say are the key next steps, both from the observational side and Wieslaw from the modeling side in terms of future work? I know ONR has this prescribed, or has this set of DRIs that they're implementing. What next in terms of what's been learned in this particular region of the marginal ice zones would you advocate for moving to downstream in the Arctic?
So I think there are a few things, right? The C-State program, which was the program that followed this, was incredibly successful. They produced a lot of beautiful results, and they were focused on primarily, surface wave climate and impacts on the freeze-up period, which was a very nice bookend to a marginal ice zone, which was looking at the melt period. Those results are out there now. They just finished off a special issue of JGR. So you can grab that, and they're really, really neat things to read there. Following that is SOTA, which is an attempt to look at the entire annual cycle, if you will. Looking at contrast between an area where it's largely ice-free during the summer, an area where it's rarely ice-free during the summer, and something kind of in the middle. And that's coming out of the water this autumn. That was the next step to try to put this all together. So those three in session were meant to couple. What I would like to see is an ability to connect the surface energy balance a little bit better, right? We don't do that. Mosaic may do that as a kind of drifting year-long process study, but it's not really a year because it's a year, but they're drifting through many different regimes. So it would be very difficult to interpret that, I think, as a single time series. So there's the atmospheric piece that would be nice to see. It would be nice to see more on ice dynamics, if you will. And then the last piece is I would like to see a multi-year campaign in the upper ocean in this region. Right? It's great to get these snapshots of things, snapshots being a few months, a year kind of thing, but it's hard to talk about a seasonal cycle, or much less how that seasonal cycle is changing, right? Unless we have consistent measurements over a longer period of time.
And just a quick follow-up in terms of so informing the Arctic Ocean Observing System or network. Do you have an audience with those that are planning this? And would that also help you with this more multi-year examination of the upper ocean? A deployment of an ocean observing network.
So we've been talking about this for a decade and a half, 2 decades now, about how to achieve this and chipping away at the edges of it. There are currently groups like SEON out there, right, that are trying to advocate for this. There's now a connection being drawn between SEON and Goose for the Arctic. I'm serving as the project rep for that effort. So I think we're making progress on that conversation. Whether that results in the kind of support that's required to implement it remains to be seen.
Okay.
I think we know how to make progress with floats.
Okay.
I think we understand how to start extending Argo into the Arctic point. It's just a matter of starting to try that. That would be a big step.
Right.
Do we have any other questions? All right. Victoria, do we want to wrap up here and then go to the panel breakout?
Yeah, that sounds great, Jenny.
Okay. Okay, great. So Craig and Wieslaw, thank you so much for presenting for us. I know it was a little bit difficult trying to schedule with all of our scheduling and you guys being away, but we appreciate you guys taking the time and presenting today. I will send out a recording of your presentation to the panel group, and I'll make sure you guys are CC'd on it in case you want to review it. We won't advertise it or anything, so it'll stay within our US CLIVAR community. Did you two have any final messages you wanted to leave with the panel members?
Nope.
Thank you for having us, and apologies for running this out late.
Same here. Thank you for having us.
Yeah, no worries. We wanted to make sure we heard everything from you guys, so that was great. So thank you.
Thank you.
Bye.